Welcome you to the lecture for 13.3. This is MGF 1106, Liberal Arts Math, and my name is Jorge. So we have four objectives. We're going to understand how to compute conditional probability. We're going to calculate the probability of intersection of two events. We're going to use probability trees to compute conditional probabilities, and then we're going to understand the difference between dependent and independent events. So the first thing is conditional probability. Conditional probability, we read it as P of F given E, and essentially is we compute the probability of event F assuming that event E has already occurred, and this is what we call as conditional probability. Now the rule for computing conditional probability by counting is if E and F are events in a sample space with equally likely outcomes, then the conditional probability of F given E is equal to N of E and F divided by N of E. So here's the first example. Assume that we roll two dice and the total shown is greater than 9. What is the probability the total is odd? So we know we have 36 equally likely outcomes. We're going to let G be the event that we roll a total greater than 9, and O be the event that the total is odd. So here we have the sample space for G, and then out of this sample space, two of them are actually odd. So the probability of odd given greater than 9 is actually equal to 2 over 6, which is 1/3. Now, if E and F are events in the sample space, then the probability of F given E is equal to the probability of E and F divided by the probability of E. So here's another example. Survey of college graduates compared starting salaries to majors. So if we select a graduate who is offered between $40,001 and $45,000, what is the probability that the student has a degree in the health fields? So here we have the table. So we have health fields, and we also have the column between 40,001 to 45,000. The one that should be highlighted is health, not technology. So let R be the event. Graduate received a starting salary between 40,001 and 45,000. And let H be the event. The student has a degree in the health fields. Now we want to find P of H given R. And here we can see that P of H and R is 3. P of R is 15. So then the answer would be 0.2 or 20%. Now, rule for computing the probability of intersection of two events. If E and F are two events, then P of E and F is equal to P of E times the conditional probability of P of F given E. Now, assume your professor has written questions on 10 assigned readings on cards, and you're randomly to select 2 cards and write an essay on them. If you've read 8 of the 10 readings, what is your probability of getting 2 questions that you can answer? So let A be, you can answer the first question. Let B be that you can answer the second question. So we need to calculate P of A and B. So that's going to be equal to the probability of A times the probability of B given A, which is the probability you can answer the second question given that you can answer the first question. So P of A is 8 out of 10 because you did 8 readings out of the 10. So the probability of B given A is actually 7 out of 9. You reduce it by 1. So P of A and B is equal to 8 over 10 times 7 over 9, which is approximately 0.62 or 62%. The next thing that we're going to talk about is probability trees. So sometimes we can go ahead and represent an experiment that happens in stages with branches on a tree. And this is what's called a probability tree. Again, assume your professor will randomly ask questions on 2 of the 10 assigned readings. If you have read 8 of the 10 readings, what is the probability that you will get questions on 2 readings that you have not done? So let A be you can answer a question, let N be you cannot answer a question, and then we'll go ahead and do the probability tree. So P of A is 8 over 10, P of N is 2 over 10. So the probability you can answer either of the 2 questions is 0.02, which is 2 over 10 times 1 over 9. Events E and F are independent events if the conditional probability of F given E is equal to the probability of F. Now, if they do not equal each other, that means that E and F are dependent events. Now, assume we roll a red and green die. The events F, 5 shows on a red die, and G, the total shown in the dice, is greater than 10, independent or dependent. So 3 outcomes, 5, 6, 6, 5, and 6, 6 give a total greater than 10. So P of G is 3 over 36 or 1 over 12. Now F, we have the sample space, which is 5, 1 all the way down to 5, 6. And then G of G and F is just 5 and 6. So the probability of G given F is equal to 1 over 36 divided by 6 over 36, which is 1/6. So we can see that the probability of G given F does not equal the probability of G, so then the events are independent. The next thing is dorm rooms. So to get a dorm room, a student will have to draw a card that has the name of one dormitory, X, Y, or Z, and also has a two-person room number or an apartment number. 30% of the available space is in X, 50% in Y, and 20% of the spaces in Z. Now, half of the available spaces in X are 40%. 50% are spaces in X are rooms, 40% in spaces in Y are rooms, and 30% in Z are rooms. So the first thing is we're going to draw a probability tree to describe the situation. Then we're going to be given a student selects a card for dormitory Y. What is the probability that she will be assigned to an apartment? And then what is the probability that the student will be assigned an apartment in one of the three dormitories? So the first thing is we'll think of the assignments happening in two stages. First, the student is assigned a dormitory, and then she is assigned either a room or an apartment. So we can see the first part is dormitory, and then either room or apartment. Now, looking at the branch that's highlighted in red, we see that the probability of apartment given Y is 0.6. Now, we see that the event a student is assigned an apartment is a union of three mutually disjoint sub-events with probabilities of 0.15, 0.3, and 0.14. So the probability that the student is assigned an apartment is just the summation of those three events, which is 0.59. Now, here's another example. It is estimated that 2% of the employees at a company use a certain drug, and the company is given a drug test that is 99% accurate in identifying the drug users. What is the probability that if an employee is identified by this test as a drug user, that the person is innocent? So here we're going to do let D be the event that the person is a drug user, and let T be the event that the person tests positive for the drug. So we want to compute the probability of the D prime given T, and that's going to be equal to the probability of D prime and T divided by the probability of T. So remember, D, the person is a drug user, so D prime, the person is not a drug user, and then T is the person tests positive for the drug. So here's the probability tree. So here we have D and D prime, and then T and T prime. So takes drugs and tests positive, does not take the drug and tests positive. So P of T is equal to the sum of those two. So first you multiply 0.02 times 0.99, and then also 0.98 times 0.01, and then P of D prime and T is 0.98 times 0.01, which essentially does not take the drug but tests positive. So here we can see that the desired probability of the probability of D prime given T is 0.331. And the end of section 13.3. Thank you.